This is slide 6 of the 2.1 lecture notes. Here we want to give an example of a quadratic function with x-intercepts at 2, 0 and 6, 0. There are infinitely many quadratic functions that satisfy this criteria. And in general, a function that has those 2 points as the x-intercepts will have the form of some constant a times x minus 2 times x minus 6. This is because if you were to set this equal to 0 and then solve for x, you see that x is equal to 2 and 6. Since the question just says, given one example, we can let a be any number we want. So for example, let a be equal to 1. Then we get the function f of x equals x squared minus 8x plus 12. And I get this simply by distributing my quadratic, doing the FOIL method. Part 2 says to use symmetry to determine the x-coordinate of the vertex. Well, we know that for quadratic functions, the vertex needs to occur in the middle of the two x-intercepts. So, in between 2 and the 6, we know that x value must be equal to 4. Well, if x equals to 4, then y value, when evaluated with the a equals 0, we get 1 times 4 minus 2 times 4 minus 6. And that evaluates out to be negative 4. We can use the information we have calculated so far to graph. The grid here is given arbitrarily. You can label the x-axis and the y-axis however you see fits. I'm going to say this is the x-axis, and this is my y-axis, right here down the middle. This being the center of my coordinate system, 0, and then I'm going to label 1 unit for each grid. The vertex is at 4, negative 4. Hence it shows up right here. The x-intercepts is 2 and 6. Now if I were to do this, then everything gets shifted off to the grid. I'm just going to relabel my y-axis so that everything is going to fit nicely on the grid. I'm going to let this left boundary be the y-axis. So here 0 shows up right here in the origin. Again, this is 1 unit's mark. So the vertex of 4, negative 4 would then show up right here. The x-intercepts of 2 and 6 will be right those points. Now if we were to connect all those dots, we get the parabola as desired. Part C of the question says on what intervals is f of x less than or equal to 0. This is looking for the x values such that your function value is below the x-axis, where all these points right here will have the function value less than or equal to 0. All of these points here will have the function value above. Looking at the graph right here, we can tell if your x values are in between 2 and 6, right here in this domain, then your function value is going to fall below the x-axis. If your x values are to the right of 6 or to the left of 2, then your function value is going to be above the x-axis. So for part C, the interval on which f of x is less than or equal to 0 is going to be 2 to 6. For part D, the interval on which f of x is positive is going to be from negative infinity, exclusive, therefore using the left open parentheses, all the way to 2. Now it's saying just positive but not equal to 0, so we have to exclude 2 on the right. Union the interval at which it starts at 6 all the way to the infinity. So negative infinity to 2 gives you this interval, and then from 6 to positive infinity gives you that interval there. This concludes this slide right here. Now we go to slide 11 in the 2.1 lecture notes. This fits quite nicely after the slide 6 explanation. This question here asks for what prices is a publisher making a profit. Well, if you look at the graph on the right, which is describing the profit function in terms of the price per book, the price at which the publisher is actually making a profit is the values of p such that your profit function sits above the x-axis. Essentially, we're looking for these x values or these p values such that your profit is positive, sitting above the x-axis. Now, it might be a little bit harder to read because the graph is so small, but that first point of x-intercept is actually at 14, and the second point of intercept is at 64. Hence, the domain or the prices where the publisher is making a profit is in between 14 and 64. And notice that I used the left open parentheses and right open parentheses because actually to make a profit, you have to have p strictly greater than 0, but not equal to. If you want to actually get the same answer by using a different graph, i.e. the second graph below here, where it's the graph of the revenue function along with the total cost function, in order to actually make positive profit, you're first looking for the point where they break even. The break-even points are exactly where the two curves intersect, and that's at 14 and also at 64. And for the points where you're actually making a profit, you want to have a greater revenue than the cost. That is exactly the portion right here where revenue is above the cost function. So the x values or the p values is in between those two break-even points. Essentially, you get the same answers using the first graph. Slide 12 here basically is a summary page of all the terms we've talked about so far, explaining all the variables, P, the demand, Q, the cost, C of Q, and also the cost, C of P. Also the revenue function, which is P times Q, and the profit function is equal to R minus C. You should review this note if you are still confused about any of the terms. Now that we've talked about the revenue, cost, and the profit function and how to maximize them, you should be able to do this one all by yourself. So take a moment and try to answer these questions on your own, and then come back to the solutions. The demand function is given where Q is the number of members in the club and the P is the annual membership fee you charge. The question asks for the total annual cost, revenue, and profit as a function of the membership price, P. This tells you that you're trying to construct C of P, R of P, and also capital P of P. To get the cost, you need to construct it using the fixed cost and the variable cost. We know that the fixed cost is $20,000. We also know that the variable cost is $20 per member. Well, if Q represents the number of members you have, then altogether you have 20 times Q. However, your goal is to construct a function in terms of P. Right now, you have the variable in terms of Q. To do that, we simply replace the variable Q using the given demand equation in terms of P. So if you do your math correctly, you get the answer 21,680 minus 1.2 P for your cost function in terms of the price. Next, for the revenue function in terms of the price, by definition, it is price times the demand. Now the demand function, again, we're using the equation given above. You get negative 0.06p plus 84. If you simplify this correctly, you would get the equation negative 0.06p squared plus 84p. Now for the profit function, which is defined by the revenue minus the cost, we take the two equations that we've computed and just plug it into its place. When you simplify, make sure you distribute a negative sign correctly, and altogether you should get a negative 0.06p squared plus 85.2p minus 21,680. In part B, it's asking for the price. We should set the annual membership fee to obtain the maximum profit. Essentially, you're looking for the optimal p-values here so that you have the maximum profit on the y-axis. This corresponds to finding the x-coordinates of the vertex in the quadratic functions denoted by p. So if we realize the profit function here as a quadratic equation, using the quadratic formula, using the vertex formula for the quadratic equations, having b value as 85.2 and a value as negative 0.06, we can get that vertex using the formula negative b over 2a. The algebra comes out to be 85.2 divided by 0.12, which is equal to 710. The unit on here is dollars. This means we should charge at $710 for the annual membership fee in order to maximize profit. The next question asks for how many members will you have at this price. The number of members is denoted by the variable q. That's the demand equation. So essentially we're looking for the q value such that when p is equal to 710. And remember to grab your demand equation from the previous slide, which is equal to negative 0.06p plus 84. If you do the calculation, you get negative 0.06 times 710 plus 84. This comes out to be 41.4. And the unit on here is people. Of course, we can't really count in decimal people, but for the sake of the problem, this would be your answer. The last part here is asking for the maximum possible profit. That is looking for the capital P value so that when the little p is equal to 710. Here you actually replace the little p in this equation with 710 to get a number. The number I got from that calculation is $8,566. And that is the maximum possible profit that this company can make by selling at a price or by charging an annual fee of 710 with 41.4 members. In the next 3 slides, we want to make a connection between what we've done so far and also the technology regression. So similar to what we did in the linear case, we were presented by some sort of data and we wanted to see what kind of fit would be good for the data. The question that we're looking at here is the annual mean carbon dioxide concentration measured at the observatory in parts per million every 10 years from 1960 through 2010. Where t equals 0 represents 1960, that's the beginning of the time period here. When t is equal to 10, that's 10 years from 1960, that will be at 1970, and then so on. If t is equal to 20, that's 1980. You could go ahead and fill in the rest of the table yourself. We want to first make a connection between what we've learned so far. In the chapter 1, we talked about how to determine when the data is linear. So in your opinion, do you think the data is linear? Why or why not? Now to take a moment and write down your answer. I would say that the table of data is not linear because if you think of this as the x value, this is the y value, and then you compute the slope between each ordered pairs of points. Between the first 2 ordered pairs of points, the slope will be the difference in the y divided by the difference in the x. And that would be 326 minus 317 divided by the 10 minus the 0. And if we do for the second set of ordered pairs of slope, you would get 339 minus 326 divided by also the 10. In the first case, you get 9/10. In the second case, you get 13/10. Clearly, these two things are not the same, If they don't have the same slopes, that means they can't possibly be lying on the same line. Hence, the data here is definitely not linear. If we plot these data points on an Excel spreadsheet along with the regression fit, you would get the following graph. The first thing we notice is that the graph is given so that the y-axis starts with 300. This is typically the case when you have large y values. In order to actually see things better in a more close-up fashion, you start with something that is not 0 in order to make it bigger to see, easier to see. I want you to make a note for this paragraph right here. When a linear model is appropriate, the data would be distributed at random above and below the regression line. What that means is 50% of the time the data should appear above the line, and 50% of the time the data should appear below the line. If you start with the first data point and the line, you see that this data point appears above the line. This one is about below, 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 and above. So 2 out of the 6 you have data points appearing above, and 4 out of the 6 times you have it below. This is definitely not a 50-50%. This is indicating that the data is probably not a linear trend. Something else needs to be done in order to model this data better. So if we use the instruction down here, it says label each data points with either plus or minus if the residual is positive or negative, then we get positive, negative, 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 and positive. And such distribution, like I said, does not appear to be randomly distributed along the line. Hence, our conclusion is that this suggests the data should not be fitted with the linear model. On the other hand, if we use the same technology and try to fit a quadratic model to the data, and the way to do that is you would click on any one of those data points in Excel, right-click it, and choose the Add Trendline option, and then choose the polynomial of order 2 in the pull-up menu. You can also include Add Equation, or include the R-squared value, however you see fit, and have it show up on the curve. This is the equation for the regression, quadratic regression, and this is the actual regression line here. Well, this time let's examine how the data points are scattered around the fit. Do the residuals appear randomly distributed above and below the quadratic regression curve? And the answer is yes. If we say this is positive, negative, and positive, and then positive, negative, and then positive, it seems that as if that the data distributed randomly above and below the quadratic regression. And so also we can tell from the SSE value, remember the sum of squares errors, for the linear model it was 58, but for the quadratic model the SSE is 2.6. And clearly that the SSE for the second, for the quadratic equation is much smaller than the SSE for the first linear equation. Therefore, we can tell that the quadratic model must be a better fit. And this concludes the discussion on section 2.1.